Alright, so today we're going to be looking at predicting enthalpy changes using something called Hess's law. Um, Now this is just kind of a way where we have a little explanation down here is that normally in a course when you've done, or if you haven't done it but soon will, done calorimetry experiments, we know that when we do stuff in like a coffee cup calorimeter where stuff are in aqueous solutions, we get really good results. Because water has such a high specific heat capacity, it's not going to lose a lot of energy to the calorimeter, and everything just works wonderfully. However, not all reactions are going to occur in aqueous solutions and are trickier to study. So some reactions take a long period of time, it may cost too much, reactants might be extremely rare, or they release way too much energy and is not safe. So when this happens, we're going to use two different methods to predict enthalpy changes and also try to find molar enthalpy for certain objects or compounds. And our first one we're going to look at is Hess's law. Now, Hess's law states that according to the law of conservation of energy, the heat of a reaction is the same whether the reactants are converted into products in a single step or a series of reactions. Because when we think about enthalpy is just or enthalpy change is just the change in potential energy. So this is where Hess's law comes in. It makes use of that idea, and it states that the addition of our thermochemical equations yields a net equation whose enthalpy change is the sum of the individual enthalpy changes. Now that just translates into this. So remember, the change in enthalpy is equal to the sum of all the enthalpy changes in a reaction. And remember, this sigma is the sum of. For those of you who haven't seen that in math for a while. So this little picture right here, this is just one that I came across, and it is true. So enthalpy doesn't judge how you get there as long as you do. So when we look at this right here, we have our reactants on one side and our products on the other. If this person decides to make a side trip over here, so this is associated enthalpy change 1, goes to McDonald's, boom, comes back, enthalpy change 2, well, it doesn't matter. At the end of the day, they are arriving as a product. So this is why delta H1 plus delta H2 will give us delta H3. And that's going to be true for all of our reactions. So it doesn't matter how many steps it takes, as long as we get there. That's it. Now, I know that's going to be a little confusing right now, so when we get there, don't worry, we'll kind of see this a little more, and when we get to our first example, it'll definitely make a lot more sense. Now, we're going to have to manipulate equations and add them together, right? Because that's what Hess's law is all about, is adding equations together, so when we add them together, we get a net equation. Now, we've seen this in net ionic equations, where we added our ionic equation and we simplified it down to our net ionic. So we've seen that before where we add stuff together, we cancel things out. Now, one thing that we haven't really seen before is that if a chemical equation is reversed. Now, we've kind of seen it, we kind of haven't, but I'm just going to give you an example here now in a sec. So if a chemical change is reversed, the sign changes. So that means if it's the delta H is a positive, it'll turn to a negative, or if it was a negative, it's going to turn to a positive. Now, an example of this is that one reaction, if we know it's exothermic. So N2 plus 3H2 produces 2NH3, and delta, and this will be a formation, is equal to, I can't remember the actual number, I think it's negative 97.5 kilojoules. Now, this is a formation reaction, right? We have element plus element produces compound. Now, we kind of made this connection as well when we were doing our review, is that a decomposition reaction is when we start with a compound and we produce the elements. So if we were to decompose ammonia, I'm going to write this in another color though, just so it's a little different. So if we're to decompose ammonia, so start with 2NH3, and decompose it into nitrogen and hydrogen. Now notice this is like literally the exact same reaction as just written in reverse. So if we were to do that, reverse a reaction, well, we would reverse the sign. So if the formation is exothermic, the decomposition is going to be endothermic, and we have the exact same numerical value. It's just the signs are different. Now, we've seen this as well when we looked at photosynthesis and cellular respiration in one of our examples back a few pages ago. So if you go back, I think that was the example after communicating enthalpy changes, where we wrote the 3 methods of communicating enthalpy change for photosynthesis and cellular respiration. And they're the exact same number of energy because they're literally reverse equations of each other. Now, also we've seen examples like this as well, where we can multiply or divide by a constant factor, and if we do that, the delta H value is altered in the same way. So if we multiply an equation by 2, we also need to multiply the enthalpy by 2. Now, to use Hess's law, there are a few rules here. So we're just going to go over the rules, and if it doesn't really make sense, it will when we start getting examples. So first of all, we need to write the net reaction of the equation if it's not given. Now, normally this is an equation that can't be directly measured. Next, we're going to manipulate all the given equations so when they add up to yield the net equation we wrote out in step 1. And we also remember to manipulate our delta H values as well. Now, once we do our manipulation, we're going to cancel and add all the remaining reactants and products just to check to make sure we end up with the net equation. Right, so this is just double checking our work, making sure that we actually manipulated everything correctly. Now, once we have all that, we are going to add all of our enthalpy values together, right? And that's where we go delta H for the reaction is going to equal the sum of all of the smaller reactions. And step 5 is optional, but you have to read the question just in case. It asks for the molar enthalpy using this equation, and that's, of course, if the question asks. So, like I said, we're going to look at our first example, and then hopefully all these will make a little more sense. Now, I know on the stuff that's printed out, we have example 1 down here, and there's an iron one, but for some reason the copy I'm using is different. It should be the exact same book. I don't know what's going on, but anyway, this is what it should read. So, if yours is a little different, just write this equation above. So it says, what is the enthalpy change for this following reaction? We have 2 irons plus half an oxygen plus water produces iron 2 oxide and hydrogen. And we need to get this equation, this net, from our 2 given equations right here. Now, when you're doing Hess's law, you want to look for unique elements or compounds in our net equation, and then try to manipulate our given equation so that they are on the correct side of the equation, and then also with the correct coefficient. So, what I mean, when we look at iron here, so we need to have iron as a reactant in my net equation. Now, out of my given equations here, equation 1 is the only one with iron. So therefore, if I use this one, this is how I can get iron into my net equation. Now here I can see iron has a coefficient of 2, and it's a reactant. In my given equation, iron has a coefficient of 2, so they match, right? 2 and 2, they match, and it is a reactant. So, based on that information, because iron is on the correct side of the equation and it has a correct coefficient, we are going to do nothing to this equation. Now, just because I'm doing nothing to it, I like to rewrite everything in my own writing just so I can add them up later. So I'm just going to take this, 2Fe plus O2 produces 2FeO, and then delta H is equal to negative 544.0 kilojoules. Now, I just like to do that, write it in my own writing, because I want to make sure if I have to manipulate this one, I get to put the arrows together and, you know, everything will look nice. But you'll see when I start adding stuff together. So you don't need to do this if you don't want to. So once I do that, I'm going to then scratch this out because I've done manipulating it. Technically, I've done nothing, but I don't want to see it anymore, right? Because if I see it, I might get confused. So I scratch it out. Now, my next one. If we look at our net equation again, now I'm just going to look for hydrogen because hydrogen is unique here and it's unique down here, right? I could do oxygen or water as well. Anyway, hydrogen just kind of jumped out at me. So when we look at hydrogen over here, hydrogen is a product and the coefficient in front is 1. On this equation though, hydrogen is a reactant and the coefficient is 2. So it's on the wrong side and it has the wrong coefficient. So I'm going to take this equation, First of all, I want to reverse it. Just because if I reverse it, now I'm going to bring hydrogen over to the product side, which I want. But I'm also going to divide by 2 so I can get the correct coefficients, meaning that 2 is going to turn into 1, this is going to turn into 1/2, and this will turn into 1. So now my new equation is this reversed, so I'm going to have H2O on this side, and I'm going to get H2 plus 1/2 O2, right? Remember, because I also divided everything by 2. And delta H, now that means I need to reverse this, so it's going to turn into a positive, and I need to divide 571.6 by 2, and I get negative 258.2 kilojoules. Done. Now we are going to check to make sure that, oh, sorry, I forgot one thing. After I manipulate it, I'm going to scratch it out so it does not come back and confuse me later. So these are my 2 equations I have manipulated. Now I'm going to add them together to see if I get my net. So we are going to, if we have the same compound or element on the exact same side of the equation, we're going to add together. If they're on opposites, they're going to cancel. Now when we look at, we have iron as a reactant over here. There's no irons as a product. There's no more irons as a reactant. So our 2Fe is going to get dropped down. Same thing with our water, because we have water right here as a reactant. There's no other water as reactant, so there's nothing to add to it. But there's no water over here as products to cancel out. So my H2O. Now my oxygen, we will notice, even though the coefficient isn't there, there should be a coefficient of 1 in front of this oxygen. I don't like writing 1 because that just looks like 10, right? But anyway, we have 1 oxygen. Now on this side, however, notice how we have half an oxygen. Now we've seen canceling before where basically everything would cancel out. But because we have half an oxygen here and only 1 here, obviously half is less, so this oxygen is going to get completely used up. Now the new coefficient in front of this oxygen, I need to do a little bit of math. It's normally a coefficient of 1. Now because oxygen is on the other side, right, we're going to subtract the half, that's what it's losing, and equal 1/2. So this 1/2 is going to get in front of this oxygen, and we bring it down to 1/2 O2. Then we go arrow. Same thing, we see iron 2 oxide, nothing can cancel out with, so 2FeO, and then plus H2. So you'll notice this is equal to this. So my net, I like to give myself a little check mark, knowing that they're the same. Now as for the delta H, what we do here, delta H is equal to, we have 2 values right here. So if you remember, I'm just going to pull up something over here. We had delta H is equal to the sum of the enthalpy changes, right? So that just means when we go back and look, we have a negative 544.0 and a positive 258.2 kilojoules. So what we're going to do is add those together. Now you don't need to show this step. If you have them, if you have them lined up like this, you can just add them together and write your number down here, right? But I'm just going to show you how that looks like when you add them up. So when we add them up, delta H for that reaction, we had our negative 544.0 kilojoules. We add this to our positive 285.8 kilojoules, and our net enthalpy change is negative 258.2 kilojoules. And this is our net change. So we take that number and we bring it over here to a negative 0.2 kilojoules. I started running out a little bit of space right there. But that is how we find the enthalpy change for our unknown. Now, I know that seemed like a lot to kind of get tossed at you in the one go. So that's why we're going to look at our second example. And then hopefully by the third you'll be able to take it and kind of run with it once we get going, and then the fourth as well. So our second example that we're going to look at, this one is more, I guess, realistic of what I expect you to be able to solve. And the reason for that is when you look at reading it, it just says determine, first of all, I'm going to point this out, it says molar enthalpy, not just enthalpy change. So determine the molar enthalpy for the formation of carbon monoxide. And we'll notice that there's no net. We're just given the evidence. So we have the formation of carbon dioxide and the combustion of carbon monoxide. So this is more realistic because you need to be able to provide your own net equation. So the net equation of the formation of carbon monoxide, we got carbon plus oxygen producing carbon monoxide. Now you do need to balance these as well. So you can use a fraction in front of oxygen, or you can just go 2 and 2, and that works. It doesn't really matter what way you do to balance it. Now, if that is my net equation, now I'm going to start manipulating. So, same thing as before, you want to try to find those unique compounds that only show up in one equation and also shows up in your net. So for our first example here, if I look at carbon, I need 2 carbons as a reactant. And carbon only shows up in this equation right here, my first one, but the coefficient is wrong. So we'll notice it's on the same side, so it's a reactant here and a reactant here, which we need, but the coefficient's off. So I need to take this equation and multiply it by 2 to get the correct coefficient in front. So that means I'm left with 2C plus 2O2 producing 2CO2, and my delta H is also doubled to a negative 787.0 kilojoules. Now for my second equation, we'll notice that our unique compound that's going to show up is definitely carbon monoxide, because we have carbon monoxide up here in my net. Now when we notice the coefficient, 2 carbon monoxide, 2 carbon monoxide. So the coefficient's fine, but the position of it, or the side, is wrong, because here is a reactant, here it is a product. So I need to take this and reverse it. So when I reverse it, I'm going to rewrite my equation. So 2CO2, arrow, 2CO plus O2. And delta H is reversed as well, so it is a positive this time, 566.0 kilojoules. Now add them together for my net. Just like before, we're going to look for things canceling out or things adding together. So let's look at carbon. We have carbon over here as a reactant. There's no other carbon anywhere in my 2 equations. So that means carbon is going to come down here unscathed. So I can write 2C plus. Next, if I look at my oxygen. So same thing as last time, we see 2O2 as a reactant and just O2 as a product. Now there's 1 here and 2 here. So obviously 1 is the lower number. So all of these oxygens are going to cancel out. Now to figure out the new coefficient for oxygen, I do a little bit of math. I got 2, right? Because 2 here minus, well, the coefficient from the oxygen over here is 1. So I'm left with a 1. So that means this is going to cancel out to 1. 1, O2. Now remember, you don't need to write out the 1. So we can just erase that and that'll be fine. Now the last one we look at is my CO2. Now notice on this side right here I have 2 CO2 as a reactant and 2 CO2 as a product. Because these are on opposite sides of the equation and their coefficients match exactly, they cancel out completely. And last but not least, for our products, the only thing that's left is 2CO. And finally, last but not least, we're just going to add our delta H's together. Now this one, if you want to show the math for this, you can, but you don't really need to, right? Because there's only 2. So you have a negative 787.0 kilojoules, and we're going to add this to a positive 566.0 kilojoules to get an overall of negative 221.0 kilojoules. Now, whenever you write out a question, always ask yourself the last question, like, did I answer the question? Now, as I pointed out when we first started this one, we want molar enthalpy. this is enthalpy change. It's not molar enthalpy. So, and I want the molar enthalpy for carbon monoxide. So, I'm not done. I need to go. Molar enthalpy is equal to the change in enthalpy over number of moles. Now, and this is going to be for CO, so the number of moles also needs to be for CO. So that means I take my negative 2 to 1.0 kilojoules, and I divide by the coefficient in front of CO, which is 2 moles. And we're left with negative 0.5 kilojoules per mole. And that is my final answer, because I know I have the correct units. So that, of course, is Hess's law. Now, once again, this is more of a realistic example just because we weren't given the equation first. Now, on the next page, it does say, once again, a more realistic situation. And by realistic, it means lab. So if you're ever doing this and you're doing research or anything like that, there's a chance that, you know, all the given equations aren't going to be nice and neat and ready for you. You need to scour some books, scour the internet, and try to find equations that you can use to manipulate in order to solve for Hess's law. So let's look at them. Now, I'm only going to help you start this question, and then I want you guys to try to finish it. And then I'll have the answer up now in a little bit as well. So if you're ever given one like this, so this one here we have 4 different equations. I know what you're thinking, like, oh my god, I have to use all 4. Well, it says right here, we can determine if we can use or discard information. All right? So when we look at this, delta H should be spaced out a lot further over here. So this is our net equation that we're looking at. So we got 2 nitrogen monoxide plus 1 oxygen produces 1 dinitrogen tetraoxide. Now, looking at this, same thing, I always like to look at, you know, unique molecules, so I see NO. So nitrogen monoxide, I know here. So therefore, I can kind of piece together that I might need to use equation 1. But you are going to notice, okay, nitrogen monoxide, it shows up in equation 2. So when you're into this situation, start trying to think ahead of the game and be like, okay, if nitrogen monoxide shows up here, and notice how nitrogen dioxide does not show up in our net, is there an equation I can cancel out nitrogen dioxide? You're like, oh, this one right here. So I can potentially use a combination of equation 1 and equation 4, right? I'm just thinking ahead. Now, if I use equation 2, right? And I use this for nitrogen monoxide. Notice how we have hydrogen, nitrogen, and water also in this equation. And when you look at our other 3 equations right here, so equation 1, notice how there's no hydrogen, no nitrogen, no water. Equation 2, there's no hydrogen, equation 3, no hydrogen, no nitrogen, no water. And equation 4, no hydrogen, no nitrogen, and no water. So that means if you use this equation, you're going to bring hydrogen, nitrogen, and water into our net equation with no way to cancel it. So if you're ever found into that, that means you're going to take this equation, take it, and omit. And that is the only way to answer this question. All right? Now, there's going to be one more equation you must omit. So this right here, you're only going to use 2 equations. So looking at that information, so the same logic I just applied to cancel out this one, because I knew I would not be able to cancel out hydrogen and nitrogen if I used it, see if you can find that next equation. And when you do, you should get an answer of delta H is equal to negative 120 kilojoules. All right, but you still need to make sure that you get this answer by manipulating the only 2 equations. And last but not least, when you guys just write this out on the side, just so you know what you do, if you do experiment or example 4, correctly, you will notice that no equations given, so you do need to figure out the standard molar enthalpy information of butane, and butane is C4H10. You should get your answer. Okay. H should be negative 125.6 kilojoules per mole. Hopefully, if you do that one correctly. All right. So try those, see if you can get those answers. If you don't, definitely make sure to contact me just so we can try to figure something out. Now, on Google Classroom as well, so I'm just going to fire this up here now in a sec. Oops, you don't need to worry about that. So on Google Classroom for our, oh, this is Chem 20, Chem 30, we will notice that I just uploaded in your classwork some stuff with Hess's Law. Hess's Law tough one, Hess's Law example in class, and Hess's Law practice, extra practice. So this here is once you complete your workbook, if you just need 5 more, just a little more practice, open up this one. It has the answers with it, but not how you actually do them out. This is the one I passed out in class. The answer's right here. Now with this one, this is more of a typical type of example that you're going to get because you need to use Hess's Law to figure out this, but you also need to figure out the molar enthalpy for hydrogen because it's basically a 2-stepper, right? So please, please, please try this one and see if you can get the answer. If you can't, once again, let me know. The answer's right here, so you should get a positive 243 kilojoules. And finally, the tough one. Now, once again, I have the answer right here. This is the one this is the toughest one I can ever find, and you will not get one like this on a diploma. It's the exact same one written twice. This is kind of one that if you're really confident with it and you want to test your abilities, try this one, right? If you get it, you know that Hess's Law will not be an issue for you. If you're still not 100% comfortable, don't try this one because it is difficult. There's no other way in it. That's why I said tough one. All right, so only try this one if you are ready. If you're not, don't worry about it. You'll never see anything this difficult in this course. I just want to give you something to really challenge yourself if you felt comfortable with it. So that's it for Hess's Law. Next is our next lesson is called molar enthalpies of formation, and this will actually be our last calculation-based thing before we have nothing but some theory towards the end, and we're actually going to tie everything we talked about so far. So Hess's Law, molar enthalpies of formation, calorimetry, communication of enthalpy, and just enthalpy equations are all going to get tied up together in basically our next lesson. So see you guys then.